Welcome to Sri Learning Academy. Let's simplify process control block. When we talk about how an operating system manages multiple programs at the same time, we often imagine the CPU jumping rapidly from one task to another. In the previous topics, you have already understood what a process is and how it moves through different states like new, ready, running, waiting, and terminated. Now, an important question naturally comes up. How does the operating system remember everything about each process when it switches between them? The answer lies in a very important data structure called the process control block, commonly known as PCB. Think of PCB as a detailed record file that the operating system maintains for every process. Just like a school keeps a file for every student containing their name, roll number, class, marks, and attendance, the operating system keeps a PCB for every process containing all the essential information needed to manage that process. Without PCB, the operating system would have no way to track processes properly. Whenever a new process is created, for example, when you double click a browser or run a program from the terminal, the operating system creates a PCB for it. This PCB stays in memory as long as the process exists. When the process finishes execution, the PCB is deleted. So you can say that the lifetime of a PCB is closely tied to the lifetime of its process. Now let us slowly understand what information is stored inside a PCB and why each part is important. The first and most basic field in a PCB is the process identification information. This usually includes a unique number called the process ID or PID. Every process must have a unique identity so the operating system can distinguish one process from another. Imagine you have 10 applications running at the same time. Without a unique ID, the OS would get confused about which process is which. Along with PID, there may also be information about the parent process. This helps the OS understand relationships between processes, especially when one process creates another, which you will study later while learning about process creation. Next comes the process state information. As you learned earlier, a process can be in different states such as ready, running, or waiting. The PCB stores the current state of the process. This is crucial because the scheduler uses this information to decide which process should get the CPU next. For example, if a process is in the waiting state because it is waiting for input from the keyboard, the scheduler knows not to give it CPU time until the input is ready. Another very important part of the PCB is CPU register information. Registers are small, fast storage locations inside the CPU that hold data like instructions, addresses, and intermediate results. When a process is running, its data is loaded into the CPU registers. But when a context switch happens, meaning the CPU switches from one process to another, the current register values must be saved somewhere. That somewhere is the PCB. Later, when the process gets CPU time again, the OS restores these values from the PCB so the process can continue exactly from where it left off. This is why PCB plays a central role in context switching, a topic you will explore in detail soon. Closely related to registers is the program counter information. The program counter holds the address of the next instruction to be executed. This value is also stored in the PCB during a context switch. Without this, the process would not know which instruction to execute next and would have to start all over again, which is clearly unacceptable. The PCB also stores CPU scheduling information. This includes things like priority, scheduling queue pointers, and other scheduling parameters. Remember from the scheduling overview that different algorithms decide which process runs next. The scheduler uses the information stored here to make fair and efficient decisions. For instance, a high priority process might be scheduled before a low priority one, and that priority value is stored inside the PCB. Memory management information is another key part of the PCB. Every process needs memory to store its code, data, stack, and heap. The PCB contains details about the memory allocated to the process, such as base and limit registers, page tables, or segment tables, depending on the memory management technique used. This information allows the operating system to ensure that a process accesses only its own memory and not someone else's, which is essential for system stability and security. Then comes accounting information. This may sound boring, but it is very useful. The operating system keeps track of how much CPU time a process has used, how long it has been running, and sometimes even time limits. This information is important for performance monitoring, billing in multi-user systems, and system optimization. For example, in a server environment, accounting data helps administrators understand which processes are consuming the most resources. The PCB also contains I/O status information. Processes often need to read from or write to files, disks, printers, or network devices. The PCB keeps track of which files are open, which I/O devices are being used, and the status of I/O operations. This ensures that when a process is paused and later resumed, its I/O operations can continue smoothly. To make this more concrete, let us take a simple example. Imagine you are typing a document in a text editor while listening to music. Both the text editor and the music player are separate processes. The CPU switches rapidly between them. When the text editor is running and you type a character, its register values, program counter, and memory information are active. Suddenly, the scheduler decides to give CPU time to the music player. At that moment, the operating system saves the text editor state into its PCB. Then it loads the music player's information from its PCB into the CPU. When the CPU comes back to the text editor, everything is restored from the PCB and you continue typing without even noticing the switch. One important thing to understand is that the PCB is a kernel data structure. This means it is stored in kernel space and is protected from direct access by user programs. This protection ensures that processors cannot modify their own PCB or someone else's PCB, which would be a serious security risk. It is also worth noting that the exact structure of PCB can vary from one operating system to another. Linux, Windows, and other systems may organize PCB fields differently or use different names, but the core idea remains the same. Every operating system needs some way to store process related information, and PCB is that way. In summary, it contains everything the operating system needs to know to start, stop, resume, schedule, and finally terminate a process. Without PCB, concepts like multitasking, scheduling, and context switching would not be possible. As you move forward to topics like process scheduling and context switching, you will see the PCB appearing again and again. Understanding it now will make those topics much easier to grasp. That is it for this video. See you in the next one.